Johannes Nicholas Bronsted was born in Bard, Denmark on February 22, 1879, and grew up in Jutland. Bronsted received his bachelor's in chemical engineering from the Technical University of Denmark in 1897 and obtained his master's in chemistry at the University of Copenhagen in 1902. Bronsted is known around the world for his work in chemistry and thermodynamics. He took over Julius Thomson's work regarding the determination of chemical affinity. Bronsted used electromotive force measurements for galvanic cells to measure the maximum work of a chemical process. He did this to ensure that the correct values were given at room temperature without an error in measurement like the calorimetric determinations had. These errors in the determinations were due to the entropy changes taking place during the chemical reaction. From 1906 to 1921, he published his findings on chemical affinity in a series of 13 monographs. When he published these results, he received his Ph.D. at the University of Copenhagen in 1908 after defending the affinity of mixing in binary systems. He later served as a professor of physical chemistry from 1908 onward, becoming university chair of physical chemistry for nearly 40 years. Bronsted is passionate about Gibbs' way of thermodynamics. In 1912, Bronsted became engulfed in the idea that Gibbs' approach to thermodynamics was a superior method. He published a short manual of physical chemistry based on the thermodynamic cycle of Carnot. He was unhappy with the classical formulation of the laws of thermodynamics. To him, heat can be considered as composed of a quantity factor, entropy, and an intensity factor, like the temperature. This way would allow the first law of thermo to be formulated as a work principle, whereas the second law would be brought into a heat equivalent principle including irreversible reactions. This approach relates thermo to physical concepts rather than to mathematical complexities. By the time of his death in 1947, no agreement had been reached with his formulations.
Bronsted developed definitions of acids and bases based on the compound's abilities to either donate or accept protons. Acids are defined as proton donors and bases as proton acceptors. Here, the acid is seen as the water, and it gives away its proton, the hydrogen, to the bicarbonate, which is the base. The determination of a substance as a Bronsted-Lowry acid or base can only be done by observing the reaction. In terms of defining acidity through the Bronsted-Lowry acid-base concept, gas phase proton affinity is defined as the negative of the enthalpy change for its association with hydrogen. The absolute or gas phase acidity of B, which is the base, is the negative of the Gibbs free energy change, while the gas phase acidity is defined for an acid formula of HA as the Gibbs free energy change.
Gibbs energy was developed in the 1870s by Josiah Willard Gibbs. Gibbs free energy combined enthalpy and entropy into a single value. He published a paper in 1873 called Graphical Methods in the Thermodynamics of Fluids, which outlined how his equation could predict the behavior of systems. The quantity is defined as G equals H minus Ts, or G equals U plus PV minus Ts. As studied in class, the general form is shown here. We can see here that is a function of temperature and pressure, making it extremely useful in thermodynamics. Under isothermal conditions, an even more useful form of the Gibbs equation is shown here. G depends on both heat and degree of system of order. If G is less than 0, a process will spontaneously occur. If G is greater than 0, the process is non-spontaneous. There are also coefficient relationships associated with Gibbs free energy, which are shown in this slide. And enthalpy and entropy are also dependent on temperature and pressure to yield these equations, which yield another set of useful coefficient relationships. From Gibbs energy, we can also create G curves to identify phase boundaries using G as a function of temperature and as a function of pressure. When the temperature and pressure is known, we can predict phase boundary conditions. Phase boundaries are lines with constant mu with the fugacity equal to 1. And this is the general and ideal gas phase boundary formula.